Thank you. So first, I would like to thank the organizers for organizing this nice meeting, and also thank you for letting me give this talk. So I'm going to report on this joint work with all of these people. So there is Nancy, Nasrin, Pietro, Luca, Tony, Pedro, Emilia, and Rosa Maria. And we started to work on this project in the previous Lefschetz meeting in Cortona. So I'm going to report on one of the results from this group work. Okay, so let us start with one homogeneous polynomial. Let's call it f. Homogeneous of degree d, let's say. Okay, from this polynomial we can construct the Hessian matrix. So this is the n by n matrix where the entry in position ij is obtained by taking the partial derivative of f with respect to xi and xj. I'm just going to use this sloppy notation. I think you know what it means. So it's an n by n matrix. And to this matrix, we also have associated a polynomial, the Hessian polynomial, which is the determinant of the matrix. So sometime in the 1850s, Hesse made a claim about these polynomials. So he claimed that the Hessian determinant is equal to 0 if and only if the variety of f is a cone. So what does it mean to be a cone? One way of saying this is that the partial derivatives of f with respect to all the n variables, these are linearly dependent. So you can see that the implication should go in this way at least. Okay, and if you're working in degree 2, it's actually equivalent. Also, Gordon and Nutter proved that this is true if the number of variables is at most 4. But if you go to 5 variables, there are counterexamples to this claim. Here is one counterexample. Okay, so here is one polynomial in 5 variables, and you can check that the Hessian is 0 in this case, but the variety is not a cone. So maybe this was bad news for Hesse, but okay, then instead we have this nice, we can study this class of polynomials now, with the Hessian being 0 without the variety being a cone. It's inspired the study of this type of polynomials. So we are going to consider generalization of this counterexample, and we call them Perazzo polynomials. Or a Perazzo form, they're always homogeneous. So Perazzo polynomial, it's a polynomial on this form. In a polynomial ring on 2 sets of variables. So we have, okay, now I'm running out of space, but we have one set of variables that we denote x1 through xn, and we have another set of variables that we denote u1 up to um. Okay. And this polynomial g and also the p polynomials here, they are polynomials in the u variables. So let's say g is homogeneous of degree d. And then the p polynomials should be homogeneous in degree d minus 1, so that f gets degree d. And moreover, I have some requirements on these. So these should be linearly independent, but algebraically dependent. The point with this is that this linear independence is going to make sure that the variety is not a cone. And this algebraic dependence makes sure that the Hessian polynomial is 0. Okay, so this is the class of polynomials that we're looking at, and we're actually going to look at the Gorenstein algebras, which have a Perazzo polynomial as the Macaulay dual generator. And I will call these Perazzo algebras. yeah, let me just write like this. So I'm going to denote them like this, and by this I mean the quotient of polynomial ring modulo the annihilator ideal of f, where f is a Perazzo polynomial. Oh, yes. Should have said that somewhere. Yeah. Anyway, characteristic is 0 throughout this whole talk. Yes, okay. Oh, and I should probably also say that we want to avoid some trivialities here. So I'm going to assume that the degree is at least 3. And I want the, let's see, the number of x variables. It should be at least 3, and the number of u variables should be at least 2. So this is just to avoid some trivial cases. Also, let's use capital N to denote the total number of variables in this polynomial ring. Okay, so these algebras, the Perazzo algebras, they do not have the strong Lefschetz property. Is it possible? I don't know how to do this. Okay, I don't know. Maybe it's a problem if I'm standing in. No. I think it's secretary. Okay, I will do nothing. Hope for the best. Anyway, so the Perazzo algebras, they do not have strong Lefschetz property, and that's because this Hessian is 0. So it's impossible to have the strong Lefschetz, but then we can ask which of them has the weak Lefschetz property. Yeah, okay. So it's because when you look at the multiplication map of Artinian-Gorenstein algebra, then you can look at it by looking at the Hessian matrix. So each of the multiplication maps is given by a Hessian matrix. Now I didn't define all of them, but you can also look at higher degree Hessians, and they give these matrices. So one of the maps will be given by this Hessian, but then the determinant is 0. Will not have maximal rank. But it might still have a WLP. Okay, and yeah, so that's the question. And from now on, I'm going to fix the number of variables to be 5, which is the smallest possible case that we can have. So now the number of x variables is 3, and the number of u variables is 2. So it's the smallest possible case, and for the rest of this talk, we only think about that case. So this assumption is for the rest of the talk. And let's also look at what happens in small degrees. So in degree 3, actually, sorry? Sorry, what? I didn't hear. Oh yeah, so it's exactly, it's the map from degree 1 to the next last degree. Yeah. And if your algebra has Sokal degree 3, then this is also one of the maps that you are looking at for the weak Lefschetz property. So for Sokal degree 3, we cannot have weak Lefschetz because the map that we want to look at is also given by the Hessian matrix. So no WP in this case. If we go to degree 4, then thanks to a result by Rodrigo Gondim, we know that they have the weak Lefschetz property. Actually, the result is for all Artinian-Gorenstein algebras in 5 variables and Sokal degree 4. So here we have WLP. Okay, so now we can focus on degree 5 and up. What happens there? That's the question. And the answer is going to be in terms of the Hilbert function. So you will be able to determine from the Hilbert function if your Perazzo algebra has WLP or not. Okay, so a starting point for our project was in a previous work by Luca Fiorindo, Emilia Messetti, and Rosa Maria Miroroy. So I'm going to state one of the theorems from this paper. So this is also in 5 variables. From now on, I will not write out n equals 5. It's always equal to 5. Okay, and they look at the possible Hilbert functions for Perazzo algebra. And the minimal possible Hilbert function is this one. So it's 1, 5, 6, and then it just stays constantly 6 until it's time to go back to 5 and 1. They're always symmetric because it's a Gorenstein algebra. And in this case, if your Perazzo algebra has this Hilbert function, then it has the WLP. And there is also a maximal Hilbert function. And let's write it like this. So the Hilbert function in K is equal to the minimum of 4K plus 1 and D plus 2, where D is the Sokal degree, up to the middle. And then after the middle, it's given by the symmetry. So you're not allowed to go higher than D plus 2. And in this case, the algebra does not have the weak Lefschetz property. Can you see when I'm in this end of the board? Okay, yeah, so the point is that we have this minimal and the maximal Hilbert functions, and we know what happens with the weak Lefschetz in those cases. But now we would like to know what happened in between. So let's look at the smallest case, which is d equal to 5. Okay, so then the minimal Hilbert function is just 1, 5, 6, 6, 5, 1. And here we have WLP. And the maximal Hilbert function, it's not allowed to go above 7. That one does not have the WLP. And as you can see, it's impossible to have anything between those two. So in this case, we are done. Now, where do I go? Maybe I can insert this one. Okay, so let's go to d equals 6. Okay, so this is again the minimal. And then we have a maximal. Which is now, now d plus 2 is 8. So the maximal will be 1, 5, 8, 8, 8, 5, 1. And now maybe I should have left more space because there are now more possibilities in between those two. But actually I'm going to focus on one of the Hilbert functions that lies in between those two. And it's this one. 1, 5, 7, 8, 7, 5, 1. This one has the WLP. And I'm going to explain why. And the reason why I chose to look at this particular one is because it illustrates the idea that we use later in the big, in a more general case. But it's more fun with actual numbers. So we're going to look at this particular one and see why it has weak Lefschetz. But to do this, I need 2 lemmas. So let's say I have a Perazzo polynomial of degree d, and then I take a general linear form and I act on f by differentiation, which gives me a polynomial of degree d minus 1. And this one is also going to be Perazzo. And moreover, the Artinian-Gorenstein algebra associated to this new Perazzo polynomial is isomorphic to this algebra. So polynomial ring quotient by the ideal I colon L, where I is the annihilator ideal of F. Yes. This L has to be generic linear form. You cannot take any. It has to be generic. Okay, that's lemma 1. And we have a second lemma which says that the following is an exact sequence. Yeah, this is an exact sequence. This minus 1 here means degree is shifted by 1. Okay, and here, of course, it's relevant that this algebra is actually isomorphic to this. Okay, so with these two lemmas, we can now analyze this one algebra with the Hilbert function in the middle. Let's see. Do I have more boards behind this one? Yes. Okay, let's use this one. No? It does not move. Okay, but maybe that's okay. What? Oh, you want to see this one? This is old news. Okay, so the point is this: if I have this exact sequence and I know the Hilbert function of 2 of the guys in the sequence, then I know also the third. So I'm going to write this in a table. So we have okay, and in this one we have this shift, so I will not use this square, I will start here. So, okay, but the point is that I want to analyze Perazzo algebra with this Hilbert function, right? Okay, and by the lemma that I just stated, this one is also a Perazzo algebra with Sockle degree 1 less. So Sockle degree is 5 here. And as I said somewhere before, there are only two possible Hilbert functions here. So we can look at these two cases separately. Let's start with this one. Okay, now I know these numbers and these numbers, so I can fill in this row. It has to be like this. So the sum of this and this should be the last row. Okay. So 1, 4, 2, 1, and the rest is 0. Okay. Now, because there is a 0 here, it means that this map that goes from, what is this, degree 3 to degree 4 here, it has to be surjective because of this 0. Because when you mod out by L, you cancel everything. So this is surjective. And then all of the other maps that comes after must also be surjective, and because it's a Gorenstein algebra, you have this duality, so it's actually enough to look at this map. And now it has the WLP. Okay, very good. So that was one case. Now we have to look at the other case where we have 6 and 6 here instead. Maybe I will be lazy and just use the same table, so I don't have to draw it once more. Okay, so we can also have this series, and now instead there should be 2 and 1 here for the numbers to add up. Okay, so what happens in this case? So to analyze this case, I'm going to draw a nice commutative diagram over here. I didn't say, but probably you guessed that this step of the map is given by multiplication by L. And here it's just the canonical map. Okay, and that's what we do here. So now we look at one instance of this sequence. Okay, and I'm also going to look at the next instance of the sequence, and then build a commutative diagram from this. Okay, now I also want maps that go like in this direction. And those are given by multiplication by a generic linear form. but not the same one. We have to take another linear form here. So multiplication by, let's say, L prime. So L prime is another generic linear form. And I would like to show that this map has maximal. If I want WLP, I want this one to have maximal rank. Okay. And okay, what is this map? So this is now a map in the smaller Perazzo algebra, which we know has the WLP already. Wait, so where does it go? It goes from degree 2 to 3, so it's actually the bijective map. It's this one. Okay, here, what is this? So this space here, it is in degree 4, so it's one-dimensional. And then you can easily prove that this map is surjective. You just have to prove that you hit something which is not 0. So this is surjective. And then by the snake lemma, the middle also has to be surjective. Which means WLP holds here. Okay. So, and those were the two cases that we needed to look at. So we have concluded that the Perazzo with this fixed Hilbert function will have WLP. And now maybe you can imagine that you can build a inductive proof out of this. So the induction would be over the Sockle degree, because you are like reducing to this algebra, which is in one Sockle degree 1 less. I'm hiding some details now, but that's the general idea that inspires the more the proof of the more general statement. Maybe I should say what the theorem is. Sorry? Yeah. There are more Hilbert functions in between. I just looked at this one as an example. But yeah, so in fact, all the other intermediate will also have the WLP, except that some of them are actually does not occur. Not every sequence is the Hilbert function of a Perazzo algebra, but those that exist, they do have WLP. So let me now find some space to state my theorem. Where should I do this? Maybe I can use this slide. I haven't used it. And maybe I'm also out of time, so. Okay, maybe just write the theorem here. So we have the WLP for these Perazzo algebras in 5 variables, if and only if. So it has WLP if and only if the Hilbert function does not have repeat the d+2s in it. So d+2 was the highest allowed number, and if you see this number twice, it will not have WLP. And the idea of the proof is that in this case, you can look at the map going between two of those d+2 dimensional components. And you can look at this represented by a higher Hessian matrix. In this matrix, you will be able to find a big block of zeros. And this is why it fails WLP. And for those that have a WLP, there is a inductive proof which uses this sort of argument that I tried to explain to you. Okay, that's it. Thank you.